Yeah. So last time, we want to get to the point when to terminate the splits. Yeah. So we do the half size split every time we split our current data size in the middle. So we reduce the problem size by 1/2. Yeah. Then after k splits, we get this size. Yeah. But then we use this formula to tell us when to stop. Yeah. We have to find the termination point. Yeah. All right. So let me just quickly recall why we get this inequality. All right. This one here means one element in the array. Yeah. When we split our problem size, we use the small interval to represent the data size. All right, so this much size, where this small interval can only cover one element. Not two. It cannot cover two. It can only cover one. Only one element left. Then you have to stop. Right? No? If there are two elements covered by this small interval, then we need another split. So that's our observation. So this inequality tells us when the problem size, the previous split, and Taylor, join us. When in the previous split, if the length of the interval is at least 1, yeah, because if the length of interval is at least 1, then there is a chance to cover two elements, right? So another split is possible. Yeah. So we need to do another split. But if the length of the interval is strictly less than 1, then we have to stop, because only one element can be covered. Yeah. No confusion. All right? Yeah. So for that observation, we derive this inequality. Now we are ready to estimate this k. Yeah. All right. First, we remove the common denominator. Common denominator, multiply both sides, all sides, by 2 to the k. Yeah. So we get this inequality. Yeah. Yeah. After, multiplication, some algebraic manipulation, simple manipulation, so we get this inequality. Yeah. Then we can take log base 2. Yeah. All right. But when we take log base 2, there is another improvement we can do when we estimate this k. Look at the less than sign here. This place, less than or equal, there is an equal case. But this place, no equal case. Okay? All right. Can we do a little better? Yeah. If not equal, yeah. Look at these two numbers, they are both integers, right? N integer, 2 to the k also integer. 2 to the k is strictly greater than n. Can we see this number is at least one more than that number? At least one more, because strictly greater than. At least one more, okay? If at least one more, yeah. Let's look at another way. Yeah. Here we want to estimate, we want to put a range on n. All right? This is the lower bound of n. This is the upper bound of n. But the upper bound here is strictly greater than n. Can we reduce the upper bound? Can we reduce the upper bound slightly? Yeah. So think about if we reduce the upper bound by 1, is it still a valid upper bound? If we reduce, yeah, so look at here. If we reduce the upper bound by 2 to the k minus 1, is this still a valid upper bound? But we can use equal sign, right? We can use equal sign, right? In that way, we improve it. We improve the element estimate because we reduce the upper bound. All right, all right. With that into consideration, all right. Yeah, yeah. So this way is this side. I haven't do the reduction, but this side I take log base 2, so I can get k minus 1 less than equal to log base 2 of n. But this side, we have a better reduction. All right? Yeah. So here we try to do better, derive worst case formula. Yeah. Because this place there is an unequal sign. That means it's not good enough. If we can get that equal sign, then that should be better. Yeah. All right. How to get that? Yeah. Based on the analysis, yeah, we have here, but this upper bound can be reduced by 1 to touch that equal sign. Yeah. After we reduce it by 1, we can touch the equal sign. All right? That's the point. All right. We touch the equal sign, then that means 2n plus 1 less than or equal to 2 to the k. Yeah. n plus 1 yeah, equals less than or equal to 2 to the k. Yeah. All right. Then we take log base 2. This time when we take log base 2, we get this inequality. The good thing is both places we have the equal sign. Both places. Upper bound, lower bound, both places we have equal sign. When we have equal sign, that means that's the best estimate. We reach the best estimate. Yeah, already we touched that equal case. That's the best, right? Yeah. If you reduce by 1 more, no, that won't be true. Yeah. So that's the reason. All right. So now we derived this inequality to estimate that k. Yeah. That k number is our worst case comparison, right? Because k corresponds to the number of splits. Each split, we need to use 1 comparison. K splits, we need to use k comparisons. So this k corresponds to the worst case efficiency number. Yeah. All right, but another thing, before we get our final conclusion, another thing we need to consider, k integer, but this 1 plus log base 2 of n non-integer, right, in general. In general, it's a non-integer expression. Similarly, this log base 2 in general, non-integer expression. The question, how do we get from non-integer expression to integer expression? We did this many times before. Yeah? Log something, but we want to get an integer expression. We have 2 simple ways, right? 2 simple ways. Ceiling function or floor function. We take ceiling function or floor function. Okay? 2 possible ways. Now can you tell me, yeah, so here let me erase, yeah, very messy here. All right, so in this expression, we want to make upper bound, lower bound, both places integer expressions. Yeah. Can you tell me which one, floor function or ceiling function, which one to use? For the upper bound, what function do you want to use? Upper bound. Upper bound. Upper bound. If you take ceiling, even bigger, right? Even bigger. All right? Because our idea is we want to make upper bound as small as possible. we want to make lower bound as big as possible. That's better estimate. All right. So upper bound, we want to make it smaller. Smaller. Yeah, smaller. So closer to this k. Right? So we should not take ceiling function. We should take a floor function. Floor function, make it smaller. Lower bound, we want to make it larger. Larger. When this expression is a non-integer, that integer k, we want to make a non-integer closer to k, ceiling function. Ceiling function. Yeah. That understanding. So we can take ceiling function on the lower bound and the floor function, because this is integer. When we take a floor function, we just apply on that non-integer expression. One integer, we take it out. All right. Then, with this inequality, then we can make our conclusion. We derive two formulas. Lower bound formula, upper bound formula. All right. Our formula 1, k sub max. I use this because the maximum number of k number of splits, the maximum number of splits in the whole process, right? In the whole process. Yeah. We use the lower bound. Lower bound, we should use the ceiling function. Okay? The ceiling function. Yeah. The second formula, we use the upper bound. It should be the floor function. All right. Here you can see the same k max, and you get two different formulas, and these two formulas are the same. Same value. Okay? Yeah, same value. Yeah. It can be proved. Yeah. This can be, so this formula is given in our textbook, in the appendix. Yeah. It can be proved. Right? Yeah. Yeah. To prove it, we can use mathematical induction to prove it. Yeah. Here I skip that step. So that is the formula. All right? So now, this is the exact formula. All right? Exact formula. Okay? If I ask you the worst case efficiency for binary search, you need to apply one of the two. Okay? Yeah. Same. Yeah. You plug in. Yeah. One of the two. That's the exact formula. So here, why I spend so much time to talk about this worst case exact formula? The reason very simple. Every semester, when I gave the students worst case efficiency question, my students always use these two formulas. Okay? Yeah. One is log base 2 ceiling function. Another is log base 2 n function. Okay? All right. Yeah. Because based on their understanding, they feel naturally they should use these two, but these two formulas very close to the exact formula, but not the same. Not the same, you can see. These two versions. Okay? Most students, yeah, based on their logic, they tend to use these two formulas. But we know the exact formulas here. Yeah. All right? Yeah. 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 For example, so here you can see. Here I want to give you a strong impression. So I'm willing to spend a few more minutes. Strong impression, because more than one half of the students got this wrong, got this question wrong. Yeah. Easy question. All right. Here, let me use n equals 512. That's the power of 2, right? Yeah. Yeah, because I may give you the question. Given an ordered array with 512 elements, now I ask you to apply the binary search on it. Tell me how many comparisons do you need for the worst case? 512. How many comparisons do you need for the worst case? Okay? Yeah. All right. If those students, if they apply these two formulas, one of the two, they will give me 9, right? Because you take a natural log, then ceiling function or floor function, they give me answer 9, but if we use one of these two formulas, what number it should be? 10, right? Yeah. The answer is 10. Use this formula. Right? Yeah. Use these two formulas, the answer is 9. You can see it's different. Okay? Yeah. So that's the reason. To get an exact answer for the worst case, you should use one of the two correct formulas. Very easy to get it wrong. Yeah. Just take log of base 2, then floor or ceiling. Yeah. So you may get it wrong. Okay. Yeah. All right. Yeah. So that's this problem. All right. Then I need to go to the next topic quickly. All right. Best case 1. Right. Worst case, we spend a lot of time to get these two formulas. Best case easy, right? First comparison, you get it. Yeah, that's best case. But next, I want to ask you, how about the average case? You have the best case, you have the worst case. How to get an average case efficiency? Yeah. Right? Yeah. Yeah. Is it, if we take average of these two numbers, best case, worst, do you think is this formula correct for the average case? Best case, worst case? Adding together, divided by 2? How about for average case? Binary search? Yeah. Incorrect. You cannot do it in this way. Incorrect. Why? Why you cannot do it in this way? Okay? Here, let me explain. You cannot do it this way. Okay? It's wrong. Why? When you take this average only under a very special situation, it is correct. Very special situation. Yeah. So that means between the best case and the worst case, here, the best case is 1. Worst case is this much. Okay? Yeah. Worst case is that much. Yeah. Between best case and worst case, if all other cases are distributed linearly like this, okay? Let's all other cases distributed in this linear way, then you can use this one. Okay? Yeah. Like insertion sort. Insertion sort, when you do insertion step, you have best case, you have worst case, then all other cases distributed linearly like that. Then average case, you can use, best case plus worst case divided by 2. But for our binary search, best case, worst case, not distributed linearly. Okay? Not distributed linearly. Yeah. Yeah. Why not distributed linearly? Yeah. Later, because when you do binary search, you do comparison based on a binary tree. Yeah. Here I draw a binary tree. Okay? This is the best case, right? On top. The bottom level, worst case. Yeah. The best case, you only have one node. One node for the best case. For the worst case, you have, in this example, you have 8 nodes. Okay, more, right? Then between them, each level, the number of nodes is different. So the distribution is in a non-linear way, right? See, it's a power of 2 way. Okay, all right. Best case, it's 2 to the 0. Then next level, 2 to the first. Next level, 2 to the second, and so on. Okay, all right. Then the bottom case, 2 to the k. Yeah. See, That's the distribution. This distribution is not a linear distribution, right? See? It's a curve. Yeah. It's a, power of 2 curve. Then you cannot use this kind of average. Right? Yeah. It's a curve, right? Yeah. So if I draw a curve, it's like this. Okay? Yeah. It's a curve. It's not a line, straight line, right? The curve. Right? All the cases distribute in this, exponential curve. Yeah. So you cannot. Yeah. All right. Then how to calculate the average case efficiency? Yeah. Next, I need to show you. Yeah. Our next topic, I need to show you how to calculate. Here, I want to use a simple example, n equals 7. Yeah. Why n equals 7 is a simple, easier example. Power of 2 minus 1. 7 is power of 2 minus 1. 2 to the third minus 1. When the number of nodes equals 2 to the k minus 1, then this binary tree corresponds to a complete binary tree. Complete. Complete binary tree, what's the complete binary tree? All the levels are full, okay? Yeah. All level, this is a complete binary tree, okay? Yeah. All levels are full. Yeah. Yeah. If the bottom level is not full, yeah, it's not a complete binary tree. Yeah. Complete binary tree, it's easier to do the calculation. Yeah. All right? All right. B.3. Now I use that n equals 7 to show you how to calculate average case efficiency. All right. I need to draw a binary tree corresponds to 7-element ordered array. 7-element ordered array. Okay. All right. Yeah. Yeah. All right. Yeah. We assume V is in the array. Yeah. Otherwise, if V is not in the array, then we need to talk about the probability, right? Yeah. Like our linear search, there is a probability P. We need to know. Yeah. Here, I want to simplify the question. So I assume it's in the array, so we do not need to consider probability P. Yeah. All right. Yeah. Yeah. Now, at the root of the binary tree, the node 4, at position 4, we should place it at the root of this binary tree. The first comparison, we compare V with this median element. All right, so that's the top level. Yeah, we need one comparison. So this one means one comparison. Right. Then 2 branches, this binary tree, 2 branches, left branch, right branch, left subtree, right subtree. The root of the left subtree, then you go to this side. So node 2 is the root of the left subtree. Right subtree root 6 is the root of the right subtree. Yeah. That's the next level. Yeah. And this level, we need each node, in order to get a match for each node, we need 2 comparisons. All right. Yeah. Then another level, 3, 1, and 3. Okay. 2 child nodes of node 2. And 5, 7. Now we get a level, bottom level. Each node, to get a match for each node, we need 3 comparisons. Yeah. So we complete drawing this binary tree. Yeah. Now we are ready to calculate the average case efficiency. After you complete drawing this binary tree, you get the information. Now we can write the final formula for the average case efficiency. All right, this is the formula. All right, yeah. So look at here. Yeah. the numerator. Denominator, we know total number of nodes, 7. That's easy. But numerator, how do we get a numerator? 1 times 1, right? 1 times 1. Yeah. The first one means, let me write the meaning. The first one means number of comparisons, okay? Yeah. So the first number means number of comparisons. Okay? For each node. For each node. In this level. Okay? Yeah? In this level. All right? Yeah. The second means the number of nodes in this level. Okay? Yeah. That's the meaning. Okay? Yeah. So the top level, 1 comparison for each node, and there is only 1 node in this level. All right? The second term, 2 comparisons for each node. Yeah. We need 2 comparisons to get a match for each node. But there are 2 nodes in this level. 2 nodes. Okay, all right. The third term, each node, to get a match for each node, we need 3 comparisons, but there are 4 nodes in this level. All right. Then you add them up. Okay? Yeah? You accumulate. So the numerator means you accumulate all the comparisons from all the levels, right? Yeah? All the levels. Yeah. Each term subtotal. Okay? Subtotal of this level. But you need to add all the subtotals. You get this numerator number. Yeah. Yeah. Then the answer is 17/7. Yeah. Yeah. All right. This example, simple example. Yeah. Yeah. Then tomorrow I will post homework assignment number 2. Okay. Homework assignment number 2, part B. Yeah. We have part A, part B. Part A, quiz number 5. Okay. Yeah. Part A equals quiz 5. I will post this weekend. Yeah. But tomorrow, I will post part B, 15 computation questions. Yeah. In those 15 computation questions, there is 1 question you need to calculate average case efficiency. 1. Only 1 question. But you need to do the calculation. Okay? But the question when I give you a little different from this one. I change a little bit. The question I will give you, let me draw something here. Assume this line segment means what's that? The ordered array, okay? Ordered array with certain number of elements. Right? Yeah. You apply binary search, you draw binary tree. But in the question, I give you a condition. The given key is not in the, from the left end, there is certain range. It does not fall into that certain range in the left end. Right end, we exclude certain range. Exclude it. Okay? All right. So the given key only falls into this part. Yeah. V is in this part. Yeah. All right. I'll give you that condition. All right. Yeah. But this condition is a hidden condition. Hidden condition. Hidden condition, that means you do not know it. Okay? That's the fact. It's a hidden fact. Yeah. It occurs when you run your program. Okay? When you run the program, you are given a key, but that given key falls into this range. It happens. You do not know, but it happens. Okay? What's the meaning of that? That means you cannot modify your binary search only for this part. Okay? You cannot modify binary search for that. Your binary search should be applied on the whole array. Okay? On the whole array. But when you calculate your average, because this left part, right part never occur. So when you calculate your average, you do not need to use the data in these two ends. Okay? When you do the calculation, you don't need to use, because these two cases never occur. Never occur. But your program, you need to apply your program on the whole array, right? Yeah, because you do not know. You cannot assume any hidden fact, right? Hidden fact, nobody can see it. In my question description, I specify that. Okay, here I just want you to be aware of it. Okay, be aware of it. Yeah. So do not just change. Yeah, because many students before they only do the binary search on this inside part. Yeah. Not that. Okay. Not in that way. Okay? Yeah. All right. Yeah. So we complete this topic. Yeah. Next, selection problem. Yeah. Our second half. Selection problem. First, I need to give you the selection problem. Describe the selection problem. The general selection problem. What's that? Very simple. Yeah. Actually, I gave you before. Yeah. So we talk about the minimum, right? Yeah. But here, let me just talk about it again. Given an array and a positive integer k, how to find the kth smallest element? That's the selection problem. Yeah. The array is unordered. You cannot assume array is ordered. Yeah. Because if array is ordered, then too easy, right? Yeah. You just pick kth smallest immediately. So, yeah. But the array, this array is unordered. Then, how to find the kth smallest element? Yeah. Similarly, sometimes we do kth largest. Yeah. Just different versions. Yeah. Yeah. So here we only need to, work on one of the two cases. Yeah. All right. And many people, when they solve this problem, they tend to, so here another name for it, we call it kth statistic. Yeah. Also, there is another word called a rank. Yeah. This k, people also call the rank, is equals 8. Yeah. The smallest, rank 1. Okay. Second smallest, rank 2, and so on. Yeah. All right. Yeah. And many people, when they work on this question, they may want to sort the array first. If you sort the array first, you do too much work. Too much work. Okay? Yeah. Sorting. Yeah. More than necessary. More than necessary. Yeah. All right? Yeah. Yeah. If we use asymptotic notation, sorting, later our best algorithm, big O of n log n, sorting, okay, n log n. You need to do this much work, okay, yeah. But solving selection problem, we don't need that much work. Solving selection problem later, yeah. Here I tell you the result. The amount of work we need, big O of n. We do not need that extra log base 2 of n multiplication. that many. You can do better than sorting way. Yeah. The sorting way is only useful when you need to do selection problem many times. Okay, many times. Then probably you do the sorting. If you only do selection problem once, then you have a better way. Only once. If you do large number of times, then sorting is better. Because you only need to sort once, right? After the sorting, then the remaining work, very easy. But here, if I ask you just do once, then you do sorting, you do too much work. Okay? Yeah, all right. Yeah. So here, let me just, explain. Yeah. So that here I do not want to talk about. So there is this linear algorithm, but that algorithm is very complicated. So I don't want to spend too much time on that. So here I just describe some general idea. Yeah. That algorithm that can do in big O of n. Yeah. The idea is divide the problem into two subproblems. Divide and conquer. Yeah. Divide somewhere. Yeah. Yeah. And eliminate one of the two subarrays. You have two subarrays. So you eliminate one of the two. Yeah. All right. Drop one of the subproblems. Okay. All right. Then you do recursion. Yeah. After you drop two, then in the remaining subarray, you do divide conquer another time, divide it into two subproblems, drop one of two. Yeah. Similar to binary search, but this one, you cannot divide the subproblem in the middle, right in the middle. Yeah. In the median. Specific in the median, yeah, middle, yeah, it's somewhere in the middle, okay, yeah, but it's here. What I mean is we cannot divide original problem into two subproblems with the equal size. Yeah. Using the median to do the division, we cannot do that. So here the problem here is how do you divide the original problem into two subproblems? That's the main focus of this question. Yeah. All right. Yeah. Yeah. All right. So here, kth order statistic. Yeah. Kth rank. Yeah. Rank is k. Yeah. All right. So, yeah. And here, when we say kth smallest, okay, yeah. Because when we consider elimination, we can consider two ends, elimination from the left end and elimination from the right end. Yeah. Two ends. Okay. Yeah. Because in this way we can do more eliminations, right? Yeah, two ends. Yeah. So we look at from the both ends. Yeah. We try to eliminate as many elements as possible. Yeah. All right. Yeah. And here, in this diagram, suppose this is somewhere we want to do the eliminate, or we want to do the split, divide the original array, split. Yeah. Then the location of this point is important. Where do you choose the point to split two subarrays? This location is directly impacts the efficiency of the whole solution. If you choose the solution not good enough, then your performance could be very bad. Yeah. So what do you mean that if the location not good? Yeah. If the location is too close to the left end, too close, or too close to the right end, this side too close. Yeah. Then remember I mentioned a principle before, balancing principle, right? I mentioned a balancing principle before. What's that? Principle. Principle. I mentioned that before. What's that? When you have a chance to split your data, the best way to split is the balanced way. Balanced way is right in the middle. Yeah. The median, but here it's hard to do the split at the location of median. It's hard, all right? Yeah. So then we try to make the split location near the median. Okay? Yeah. We try to avoid this split point too close to the two endpoints. Two endpoints, that's the most unbalanced splits, right? Yeah. So we want to avoid the unbalanced split. Unbalanced split to get a better efficiency. Yeah, here we use that idea. Okay, all right. So, in order to do that, yeah, then how do we avoid unbalanced cases? Yeah. So we try to get left portion, right portion eliminated. These two red circles, we want to eliminate these two unbalanced situations. Yeah. Yeah. Then, so our split point, it should be located, in the inside part. Yeah. Inside part. Yeah. All right. So here I described the idea of that algorithm. Yeah. But if the question, yeah, how do we get these two unbalanced cases eliminated? Yeah. So later, yeah, by the algorithm, you will see. Yeah. 3/10 of the array size, 3/10 of n. Yeah. Left red circle, the size of it, 30%. 30% of the elements can be eliminated. Okay? All right. Right, also 30% of n could be eliminated from the right side. Yeah. Yeah. Then we avoid poor worst case. Yeah. Yeah. All right. But the question here, yeah. Let me use another slide to quickly describe how to avoid 30%. Okay? Yeah. There is a smart idea. Here, I just describe it. Okay. Detail, you can read the textbook. It's in our textbook. Yeah. But it is very complicated. So here, I do not talk about the whole algorithm. But I give you some high-level description of the algorithm. Here, I only tell you how to split, how to get that 30% of the elements eliminated. All right. The idea is very interesting. Give n elements, okay? Yeah. We group these n elements, yeah, all right, in this way. Put 5 elements in one group, okay? Yeah. Another 5 elements, second group. Okay, and so on. Yeah. To group all of them. Okay. Yeah. All right. Then keep doing that grouping. Yeah. Okay. Until we exhaust all the elements. Okay, all elements, probably you have a few more. Okay, yeah, because it may not be multiple of 5. All right. Then its next step is find the median of each 5-element group. Find the median. Find the median. Okay. Yeah. Next example, I will do it. I will solve the median of 5 problem. Okay. Now, next question. Yeah. All right. Find the median. We know the solution is 6 comparisons. Okay. All right. Suppose this is the median. This one median, M1. Yeah. In that algorithm, after you find the median, you know which 2 is above the median and which 2 is below the median. That algorithm will tell you. Yeah. 2 elements above the median, 2 elements below the median, so you get a median. Okay, 6 elements. Then, second group, you find the median, M2, another 6 comparisons. All right, that and so on. So each group, you find the median K. Okay. All right. Yeah. All right. Then you look at all the medians, all the medians. Okay, all the medians. Yeah. You'll find all the medians. All right. Yeah. But you need to do another step. Find the median of these medians. Okay? Another recursive function call. You do recursion. Yeah. Find the median. Median. You have a function. Find the median. Okay. Yeah. So here you do recursion. Yeah. Recursion. Recursion to find the median of these median. Okay? Yeah. 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 Somewhere here, okay? Median of median. After you get that, median of median, then you can do the elimination. Okay? Yeah. A lot of left and right end, 2 ends, elements can be eliminated. This part, 30% of the n, approximately. This part, also 30% of the n. Then you reduce the problem size, right? Yeah, after elimination, you know. Yeah. 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 All right, so that's the general idea. Yeah, yeah, but I do not want to spend too much time. Yeah. Yeah. But the final result, result is you have the linear algorithm for the selection problem. Right? That's big O of n. Okay? Without sorting. Okay? So you only need to know this conclusion. Okay? It's available. The algorithm is available. Okay? All right. Yeah. Next, I need to jump to an example, important example. Okay? Find the median of 5 elements. Here I use x1, x2, x3, x4, and x5. Okay, all right. Last time, yeah, this is our, final basic result, number 6. Yeah. Last time we did 5-element sorting. How many comparisons do we need to sort 5-element array? Last time we did that. Still remember that? Sorting 5 elements. How many? Close. Try to get close. 7. 7. Okay. Sorting 5, 7 comparison. Okay. All right. Then finding the median, we should do better than 7, right? Otherwise, we can sort it. Then we pick the median immediately. Yeah. So we should do at least 1 better than 7, right? Yeah. At least 1 better than 7. So we should target 6 comparison to find the median. Okay? All right. Solution. Yeah. Here I give you the answer, 6 comparisons. All right. Now, let me show you the solution. Show you the solution. Okay? All right. First, this question is a hard question. Okay? It's a hard question. Yeah. The difficulty of this one similar to that sorting 5-element array. As hard as that. Yeah. But without any knowledge in this class, if you ask, some of your friends working in IT industry, they may not have the knowledge of our class. Ask them solve usually many hours of work. Many hours of work. If they can solve, that's good. That's very good. All right. Now, because this is module 4, so we build up. Yeah. So we have learned the knowledge in these 4 modules. Now we have the sufficient background, so we can solve the problem not that hard. Yeah. All right. So let me start. Okay. The first round, tournament method. Yeah. That's the easy part. Okay. All right. Round 1, tournament method. All right. All right. X1, X2, 1 comparison. Let's assume X2 is the winner, X3, X4, X4 is the winner, second comparison. Then another comparison, number 3, let's assume X2 is the winner. Okay, after 3 comparisons, yeah. Let's draw a diagram. What do we have so far at this point? X2, X3, X4, X1, right? Yeah. Okay. Then, round 2. Elimination. Which element can be eliminated from, consideration for the median? Which element, when you look at this diagram, which one cannot be the median? X2. Because X2 greater than 3 elements. Okay? Greater than at least 3 elements. So we get cannot be the median. Okay? Yeah. Because greater than 3 elements. Because the median here equals third largest or third smallest. Okay? Yeah. Median, we know median of 5 here, median of 5 equals either third largest or third smallest. Okay? One element is greater than at least 3 elements, then cannot be the third smallest. Okay, that's simple. So eliminate it so that it is gone. Okay, all right. Then let's do round 3. Round 3. Right. What do we have so far? We have after elimination, x3, x4, x2 here, and there is x5, unknown x5 here. Oh, sorry. Oh, okay. Yeah, some problem. All right. Now, we need to do comparison number 4. Which 2 elements you want to compare as comparison number 4 for round 3? Oh, before we do that, let me give you another important fact. Point out that important fact to help you answer that question. Comparison number 4. What fact? Original median. That original median equals after elimination. After elimination, we only have 4 elements left. Original median, if you look at in this 4 elements, it must be in this 4 element array, subarray. Can you update? It won't. So in these 4 elements, you eliminate. So let me draw a diagram here. Okay. All right. 5 elements, right? Median is this one, right? Median is this one. But now you eliminate 1 element that is above the median, right? One of the 2. One of 2 gone, right? One of the 2. The top 2. You eliminate one of the top 2 elements. Then original median becomes second largest, right? So original median is second largest in the remaining. Oh. Part. Okay. Yeah. All right. Median. We update. Now, after you observe this fact, now we need to find second largest here, right? We need to find second largest element here. Now I ask you, what is your comparison number 4? Go second largest. Which comparison you want to do? For the x5, x3? Although you can try, but here, look at the situation. We did find the second largest element in 4 element array, right? Remember? It's one of our FBR question, right? We did that. Right?
Are you saying that x1 is the same value, or are you saying that
Oh, sorry. X2 eliminate. Yeah, you're right. Sorry. So that's wrong. X1. X1 should be here. Because X2 eliminated. Now look at. So a better way is we apply our comparison number 4 here. X1 and X5. Why? Because is it like a tournament method? one pair, one pair. You do comparison here. That part of the tournament method, right? Part of the tournament method. But we do not need to do this comparison. This comparison is given. Okay? Not given, so we do our comparison of tournament method. Okay? All right. Yeah. And you know how to find the second largest. You know how to find, yeah, in our, yeah, later, yeah, here I give you a formula. Yeah, next time I will derive this formula. Find the second largest there is a formula n plus base 2 of n minus 2. Okay? This is the formula. Yeah. Next class I will derive this formula. Okay? Yeah. Here I give you this formula. Although we did this, we used 4 comparison before. Okay? We did on 4 elements we used 4 comparison before. If you plug in 4 and 4, you also get 4 comparison. Okay? Yeah. Find second largest elements. In a 4-element array, we need a 4 comparison. But this comparison given, right? This comparison already given. That means one of the 4 comparisons is given. So you can save this comparison. Okay? This given comparison can be saved. Then you only need 3 more comparisons, right? So in our round number 3, we just need 3 more comparisons. Three more comparisons. Okay? Yeah. Yeah. All right? Yeah. So first round, second round we just do elimination. So now we combine all the comparisons, 3 plus 3, 6 comparisons. Okay? So total here, 3 plus 3, 6 comparison. Question? Question? Yeah. 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 Here, this formula, because we know how to find second largest. Yeah. So here I just do not repeat the whole thing. Yeah. We know we have it. Yeah. And we did that before. But we can save one of the comparisons. This one, we don't need to do it. We repeat the original algorithm, but when we get here, we don't do it. We have the result. Okay. Then we keep doing the remaining things. Okay? Yeah. That's why we only need 3 more comparisons, not 4. Okay? 4 unknown information. We don't have any information. Then we need 4. Okay? But the one of this information can be reused, right? So it can save us 1 comparison. Yeah. All right? Yeah. All right, so that's it. Tomorrow, I will post homework assignment number 2. Okay? Check the canvas. Yeah. So then, Thursday, I will complete part C. Part C. Merge sort.